So, as we are discussing about this piezoresistive sensor, and we already know that the arrangement or the alignment of the resistor actually matters, like how whether this is aligned along the radius or in transverse direction to the radius, right. And let us say this is the membrane and uniform pressure P is applied on the diaphragm. Diaphragm pointing to the normal to the paper. Now, the stress component, that is, let us say sigma x. So, sigma x is the stress in x direction, which is working radially, which is directed in this direction, right. Sigma x is in this direction. So, that sigma x is equal to P into A by H whole square, and that we find, that we are writing from this expression, right, from the plate theory. Now, as we have discussed for Poisson ratio, that whatever is the stress in in x y direction will be just the Poisson constant into sigma x. So, sigma y is equal to Poisson constant in nu to sigma x, that is nu into P into A square by H square. Now, nu is 0.3 for silicon. So, if it is a silicon membrane, we can consider nu to be 0.3. Now, this is the sigma x, and as you can see, this is the direction of the resistor also. It means it is the longitudinal direction of the resistor. So, longitudinal stress sigma L is equal to actually sigma x, right, and transverse stress sigma T is equal to sigma y. But let us say if the resistor was mounted or fabricated like this in this arrangement, then sigma L would be equal to sigma y actually, right, if the arrangement was like this. So, this actually does matter, because sigma y and sigma x is not same, right. So, sigma L and sigma T is also not same. So, we can write that sigma L is equal to P into A square by H square, and sigma T equals to nu P into A square by H square. Now, earlier we have seen that delta R by R can be represented as the gauge factor into strain or the piezoresistive coefficient into stress, right. So, we have already the stress values. So, we can write So, as I mentioned that this piezoresistive coefficient is have a directional property. So, along the length, the piezoresistive coefficient along the length and like in the longitudinal direction or in the transverse direction are not same. So, delta r by r will be having both the components. So, this is the longitudinal component, which is piezoresistive coefficient in the longitudinal direction into stress in the longitudinal direction, plus piezoresistive coefficient in the transverse direction into stress in the transverse direction. For single crystal silicon membrane, along 110 direction, we can consider that pi t is equals to minus of pi l. So, delta r by r becomes then pi l sigma l, and then this minus will come minus pi l nu to sigma l, right, because sigma t is again nu into sigma l. Delta r by r is equal to pi l p into a square by h square into 1 minus nu, right. So, we are putting sigma l value is pi p into a square by h square, and then we are taking pi l into p into a square by h square common, and we have then 1 minus nu. And what will be the corresponding strain? Then is equal to sigma by y, or y is our Young's modulus. So, this becomes p into a square by h square into 1 minus nu divided by y. So, in terms of gauge factor, delta r by r in terms of gauge factor will become g into epsilon. So, that is g by y into p a by h whole square into 1 minus nu. So, both the piezoresistive both the expression with piezoresistive coefficient as well as with the gauge factor are important. Now, we know that this is our membrane. So, this is our membrane, and we have the piezoresistive elements here. 4 different resistors are actually put here. The pressure is coming. And because of that, the membrane will deflect, right, and So, this is the top view of the membrane. This side is, let us say, 2A, and we have then 4 different resistors, piezo resistors. This is, let us say, R1, R2, and R4. We have measured the stress and strain along this axis, right, and then it is connected like a Wheatstone bridge. So, this is where I am measuring the output voltage V0, and then actually applying some voltage. This is V in. Now, what we have taken, that this all the initial resistances are same. So, R1, R2, R3 and R4, 2 equals to R3 equals to R4 equals to R, let us say. Okay. Then V naught, the output voltage, is equals to delta R by R into V in, right. And now I know what is delta R by R. So, delta R by R is P into S square by H square to 1 minus nu into pi L V in. So, by measuring the output voltage V naught, we can calculate the P. Now, in this expression we are actually applying this V in and then measuring the V naught, right, and using V naught we know that how much is the pressure, we can back calculate the pressure. Now, if the pressure changes, then also V naught changes, and if the V in changes, then also V naught changes, right. So, the sensitivity is defined as S is equals to delta V naught by delta P. Technically it should be the sensitivity, that how much is the output voltage changes with per unit change of delta P, but here will be on V in term also, because if we change the V in, then also we can get higher V0, like if we increase the V in, then we can get higher V0. So, this is per unit input voltage, sensitivity per unit input voltage. This is equals to pi L into S square by H square 1 minus nu. Now, this A and H are our geometry, depends on the geometry of the membrane, and then this pi L or nu are like depends on doping concentration, material properties, etc. So, these all we can decide, and accordingly we can select the sensitivity of the pressure sensor. Now, in this context we need to know another term called burst pressure. Burst pressure is the pressure where the what is the like burst pressure is the pressure what maximum pressure can be applied on the membrane. So, if we apply more than P burst, or burst pressure, then the membrane will get damaged or membrane will burst or membrane will break. Okay. So, burst pressure sigma max so definitely at burst pressure or the maximum pressure the stress will also be maximum like just before breaking, and then sigma max is equal to P max to A by H whole square. At this pressure, this will be the, at the burst pressure the stress will also be maximum, and this sigma max is equal to 7 GPa for silicon, 7 gigapascal. So, the point is here that we know the material sigma max, or what is the maximum pressure material can withstand. So, accordingly if we know the material geometry, then we know that how much can be the maximum pressure this pressure sensor or this membrane can withstand, because if we apply more pressure than that, then the membrane will burst. And another point to note here, that this P burst or P max is different for different geometries of membrane. Okay, so it is not a constant term for a material. Constant is sigma max, like what is the maximum stress it can withstand, but even if the sigma is constant, for different silicon membrane can be of different size. So like one membrane can be of 10 micron with 1 micron thickness, another membrane can be like 100 micron with 1 micron thickness, and both the cases the maximum capability of withstanding the pressure will be different. Just to mention here, as we are mentioning about this pressure term, that 1 atmospheric pressure or 1 atm is equal to 1 bar, and that is equals to 10 to the power 5 Pascal. Okay, and in 1 GPa is equal to 10 to the power 9 Pascal, 1 gigapascal, 10 to the power 9 Pascal. So that means 10 to the power 4. So another thing what we need to understand from this, that if we decrease the H, that is the thickness of the membrane, then sensitivity is more and more higher, or even if we increase the size, then also sensitivity is higher. But if we make the membrane very thin, then sigma max is constant, but here, so P max will also decrease, so the burst pressure will also decrease, right. So it is kind of a trade off we need to do, like what is the maximum we can make it thin so that we have a significant amount of sensitivity and without making the membrane to get damaged, right. So here you see P max only equal to sigma max into H by A whole square. So you can see that even though the sensitivity will increase if we decrease H, but the P max will decrease. So the range of pressure for which it can be used will be lesser. So sensitivity and range, these two we need to kind of optimize, that what is the for which range we want, and for that what kind of sensitivity we can achieve by controlling the other terms also, like area, then the piezoresistive coefficient, etc., and also V in is also in our hand. And another thing is, usually whatever is the maximum pressure the membrane withstand, we use 1/5 times of that. So even though let us say it can withstand withstand 10 atmosphere pressure, but we will not push the membrane to be used for 10 atmosphere pressure. Rather we will work in like the range will be decided as like 2 atmosphere maximum. Now another problem in in reducing the thickness too much is that actually the pressure and the deflection of membrane is related by this expression. So P is equal to Y, that is Young's modulus, into h to the power 4 by a to the power 4, or h is the thickness of the membrane and a is the each side of the square membrane, is equals to G1, which is a coefficient, into W0 by H plus G2 into W0 by H whole cube. So this W0 is the deflection of the membrane, and for all the real cases where we actually deal with small deflection, we can neglect this term, we can neglect this cubic term, because W0 by H will be like W0 will be very less than H, so W0 by H whole cube will be even much smaller than 1, so we can neglect that term. But if we make the membrane very thin, then this non-linearity kicks in, because then we cannot neglect that term. So this will add extra complexity to our device, and this G1 is equals to 4.13 divided by 1 minus nu square. So if you put silicon value, then it will come as 4.54, and G2 is equals to 1.98 into minus this will be 2.33. And if you put different values, like let us say I put some particular values like A by H, let us say equals to 25, and then W0 by H equals to 0.1, then we get pressure equals to 2.2 bar. This is for silicon. So for Y also you will use silicon value. Now you see why I wrote this actual numbers, because A by H is like 25. So if your membrane thickness is like 1 micron, then the side is 25 micron. So it is a pretty reasonable assumption. Then we have W0 by H equal to 0.1. So in usual case we will consider that the deflection is maximum 1/10 of the thickness. So W0 by H will be 0.1. That is also a very reasonable assumption for non-linear cases, right? So and in that case W0 by H cube will become 0.001. So that we can anyway neglect. Now this itself gives 2.2 bar, and 2.2 bar means 2.2 atmospheric pressure, means whatever is our ambient pressure now, 2.2 times, like 2 times more than that pressure is can be achieved with this kind of configuration itself. So we can pretty reasonably assume that if our deflection is not much, that we are in the linear zone. So, this is the pressure sensor we are talking about. Now, how we can make it? Okay, so first there is step by step process we need to follow for that. One is, first step is anisotropic etching of top silicon. Isotropic etching of silicon to realize the membrane. Then boron implant in particular regions using lithography, as we have discussed in last module. Of the piezoresistors. Then connect the resistors in Houston bridge and finally bond bottom wafer. So, bonding is a technique by which we can actually join two different silicon wafers. We have not discussed it in the course of in this course, but this you can consider as like gluing two different wafers. Though it is not, we do not use physically any glue, we use anodic bonding or like high temperature, high pressure bonding, where two silicon wafer will be joining to each other. So, here as you can see, this top wafer is the where the membrane is there, right. Top wafer has the membrane and it has all the resistors, all the devices made that, but the bottom side of the other half, the bottom half is actually containing that pressure probe, and how they are connected, like we cannot etch material from inside. So, first we make this material, this wafer, and then we separately make the other black bottom wafer, and then we just join them together. You can think it of like clamping two wafers together, and then we have a vacuum or like air trapped space in between, which will be like trapped gas, and then the top side or the thin side act as a membrane. Now, how we can make it, now we will discuss. Now, we will start with a simple (100) silicon wafer, and then we will deposit oxide in thermal oxidation technique. So, then in thermal oxidation technique what will happen? The oxide, both the side same thickness of oxide will grow. So, let us say this is oxide. This is oxide, and then we will spin coat photoresist, as we have discussed during the lithography class. So, we will spin coat the photoresist. Let us say this is the photoresist. And then we will use the mask to expose a particular region of the photoresist. Let us say this is the region of the photoresist what we are exposing. So, after exposure of to UV and then development, what will happen? This region of photoresist will go away, as we have discussed, right. So, then we can remove this region of photoresist so we get something like this. Okay. Okay. Now, so this is PR or photoresist and this is SiO2 silicon oxide and this is silicon. Now we use HF or buffer HF, which is a solution of hydrofluoric acid, and that HS SiO2. So SiO2 where it is exposed, that region will get etched by the buffer HF, but this region will not get etched. So then HF, so from this region the HF will get etched and SiO2 will get etched, and the other two sides which is protected by PR, there the SiO2 will be there. Now what we will do, we will do anisotropic etching using KOH or TMH, and after anisotropic etching we will get anisotropic etch profile. So how will it look? So these sides will not get etched because this is protected by the SiO2, right? But from the middle it will etch like anisotropic way, and this is the 54-degree angle, 54.7-degree angle which it creates. Now we will stop the etching at a certain distance from the bottom. So we have a thin membrane in between the other side, like the top side and the like the bottom side and this cavity, right, and this will act as our membrane. Then we will use we can use again buffer HF and acetone to strip off all the SiO2 and PR, and we remove all SiO2 using HF or that kind of solution and PR, that we can remove PR by using acetone, and then we get only the silicon structure like this. And this is the membrane. Now on top of the membrane, now let us say this is the cross sectional side and this is the top side, and this is the membrane. So we irradiate this sample from the bottom, and then we can see the light coming out of the membrane, and like that we can actually identify the membrane, and then on top of that we can again put photoresist and do lithography to put all the piezo resistors. And how do we put the piezo resistors? That is, we will open few spaces using lithography, and then we will just dope boron into those spaces, right, and then this will become, these places of silicon membrane will become piezo resistors. So we can align it like this, or we can put the piezo resistor according to our design requirement. So this is the real image which was made by Professor Ken Bhatt in Professor Ken Bhatt from IIT Bangalore. This is the real optical image of the top side of the diaphragm, and these are the piezo resistors. Here you can see these are the piezo resistors, and this is from the bottom side, and here you can see the cavity. This dark space is the cavity where light is not reflecting, so that you can understand, and this is the membrane. Now once we have this structure with once we have this structure with piezo resistors made on the top like this, So here the piezo resistors are made. Then we take another silicon wafer or glass plate where we have a hole in the middle, and that wafer actually we can put at the bottom. So that wafer we will put at the bottom, and then there will be a pressure port actually like bond this wafer to the top wafer. So this is like all the silicon, all the piezo resistors and etching has been done on this plate, and then we have a cavity at the bottom, and then we just take another plate and stick it together or clamp it together by bonding, and then we have the full pressure sensor. Now there are some important points we need to remember regarding this single crystal silicon, piezoresistive elements. That is like while we are doing this on single crystal silicon, then they are very good conductor of electric current, right. So the there is poor insulation, very poor isolation So as I told that the piezo resistors need to be connected like a Wheatstone bridge circuit, but in that case like what it happens is, as all the piezo resistors are made by doping silicon in different regions of the same silicon membrane, and if the silicon is not very good insulator, like if it, as we know the silicon is basically a semiconductor, and then there is electric charge carrier flowing in between one piezo resistor to another piezo resistor, then this will hamper the actual result. So this is one of the issues. Then temperature coefficient of sensitivity. So this nu, pi, all these factors actually depends on temperature also, and also the resistance itself like resistivity etc. also depends on temperature. So this is another problem with this kind of piezo resistors. And as we use always like most of the time we prefer p-type piezo resistors because they have very good gauge factor, so the membrane need to be n-type. N-type. So one kind of solution can be thought for this purpose is polycrystalline piezo resistors on oxide. So what we do, we have the membrane like this as we have already discussed. So this is the membrane. This is the membrane, and then rather than putting the piezo resistor on top of the membrane directly, we put a oxide layer. And then on top of that we put the piezo resistors like polycrystalline piezo resistors. So these are the 4 piezo resistors. So now these piezo resistors are actually on SiO2. So these are properly insulated from each other. Only where we will make the connection, there only they will be connected. Otherwise it is not. And but the problem here is that these polysilicon piezo resistors have low gauge factor like 30 or so, whereas the usual single crystal piezo resistors have a gauge factor around 80. So that is one problem, but one kind of advantage is there, the temperature sensitivity can be reduced by using zero doping. But one advantage of this another advantage of this technique is temperature sensitivity can be reduced by doping, reduced to almost 0 by doping. So now we have seen that how a pressure sensor can be made from scratch, starting from a silicon wafer, then doing silicon etching, then lithography, and then finally bonding two wafers to make the pressure sensor. And this is we have already seen, this is how the resistors are connected in Houston bridge connection, and this is the membrane. And then all these resistors according to the Houston bridge are actually connected to some external pads where from the electrical contacts will be taken. So these are like metal contacts. So these metal contacts are made by sputtering or physical vapor deposition, whatever we have already discussed, and then in this pressure sensor will be ready. And this is the photograph of the pressure sensor chip. So this is optical micrograph actually. Here you can see the resistors. So these are the actual boron doped resistors, and then these are the metal contacts which are connected to this contact pads, and this is the membrane region, and there you can see some marks which are actually for alignment, because as you have seen that the etching of the membrane happens from the bottom, whereas the top side actually these resistors are made. So because of that, to match the membrane and the resistor so that it is exactly placed at the space where it is required, we need these alignment marks. This is circuit diagram of the MOS integrated pressure sensor. So this is the Houston bridge. So we know that this is the voltage output what we are getting, right, and this voltage output actually like we don't need much electronics for to measure that, but still we can use a simple differential amplifier and amplify the gain, amplify the voltage output. Let us say if we are using 10 gain amplifier, then if we are getting like 2 millivolt output from the Houston bridge, then ultimately while the measure end we will see 20 millivolts. So this kind of electronics also we can put with the pressure sensor, and this will actually increase our sensitivity from by electronically. And then we can we will actually package the device. So this is the schematic of the packaging, and there we have put a header cap so that we can remove it like if air or moisture is not is harmful for our device, then we can remove the air or moisture from this part, and then like we can package it under vacuum, and we can take the leads out for our applications. And this is the final device, packaged device, which are made by Professor Ken Bhatt in IIT Bangalore and also in IIT Madras. So there you can see the actual photograph of the image of the pressure sensor. So these are the wires which are going out, actually shoulder wire, and these are the polysilicon resistors. So this is actual optical microscope image, and this is the metal pads which are actually gold pads. You can see the gold pads here, and this is the package device. So this is the top cap is open here. You can see the die, and then this die is connected to different contact points, and the pressure port will be connected here. So this is the final device, and this is the output voltage versus pressure. So as you can see that with input voltage of 1 millivolt, you can get a sensitivity of 1.8 millivolt per bar. So if our output is about 1 millivolt, then we know, if our output is about 10 millivolt, then we know that the pressure is about 1 bar, whereas if it is about 20 millivolt, then we know that it is about 10 bar pressure. So the sensitivity is 1.8 millivolt per bar, whereas if we are using 2 millivolt, then you can see that the slope is little bit increased, because as we have seen that in the sensitivity part Vin also comes. So if the input voltage is 2 volt, then in that case sensitivity is 3.6 millivolt per bar, and this is the membrane. So these graphs are drawn for this membrane thickness. So that's all for pressure sensor, MEMS pressure sensor. Thank you.